joint work with John Duffy, and we examine the impact of an anticipated liquidity constraint on savings behavior. So an anticipated liquidity constraint is when you know that tomorrow you won't be able to borrow. So it's an intertemporal optimization task that we have. And intertemporal optimization, well, it's important that you save and borrow over your lifetime in order to maximize your total utility, especially if your income is uncertain. And this is exactly what the buffer stock savings model describes. So individuals face an uncertain income, and they should target a certain ratio of wealth to permanent income in order to smooth consumption and to maximize total utility. And what we present is a lab experiment that examines the role of both an anticipated liquidity constraint, where we can turn it on and off, and income uncertainty. So income uncertainty is either high or low. And we look at the individual savings behavior in a simple 3-period buffer stock setting. So what we have is 3 periods, and this is the shortest time span where we can observe the anticipated liquidity constraints effect. So liquidity constraints prohibit you from borrowing. There's either no borrowing at all or only up to a certain amount. And what we will do in the experiment is that we will prohibit subjects from borrowing at all. If you know that you will face a liquidity constraint tomorrow, this should make you save more today. So you must self-insure against this, this constraint. And when I look at the numbers in the empirical literature, this is just one example. Boar and co-authors find that about 82% of US homeowners are liquidity constrained. You can see that potentially many people are affected. So that's important to examine how people behave under liquidity constraints. Liquidity constraints are difficult to identify in the field. So we don't have that problem in the lab, so we can just impose it on the subject. So I think that's nice. Our experiment, I think, is the first to examine the role of liquidity constraints. So we have a treatment with and without, and we can contrast it. Okay, of course, there's a lot of literature on liquidity constraints, and the buffer stock savings literature. There's one flavor that comes without an explicit liquidity constraints. It works via impatient consumers or households. That's by Carroll. Evidence is mixed, and there's one that is more closely related to ours that's with an explicit liquidity constraint. There's less literature than on the previous literature. I only found less papers, and mostly in favor of it. I think still we can contribute to the literature. And when you look at the savings and consumption smoothing literature in the experimental literature, then there are also examples. And one example is Meissner. Thomas Meissner found that people or subjects are debt averse. That is something we find in our data as well. So that's why I mentioned it. Okay, what do we find? We test all the comparative statics predictions of the model, and we cannot reject all but one. So we find that subjects do not save more in the anticipation of the liquidity constraint. And in what follows, we will explain this departure. And during this presentation, I will only focus on the depth aversion part due to time constraints. But we also examined other things, say individual characteristics. So if you score high on a CRT, on a cognitive reflection test, then you deviate less. And if you're more risk averse, then you save more. We also find that subjects learn over the course of the experiments, and then they reduce their deviations by about 15 to 25%. But I will only look here at the depth aversion part, and I will mostly focus on what's going on in the first period. So I will show you the general framework. We will derive the savings functions. Then I will show the experimental design. I will come to the results, and that's basically it. So we have a 3-period optimization problem, which is a life cycle. And in the first 2 periods, the individual can save or borrow. And in the 3rd period, the individual only consumes, does not take an active decision. So we need that in macro terms to close the model. And I will just show you what's going on here. So in the first period, you receive an income, Y1, that's according to this discrete uniform distribution with a minimum and maximum income that's easy to communicate to the subjects. You take your saving and borrowing decision. You determine basically your consumption choice, and you receive utility, and utilitying is according to this log utility function. And the second period, again, you receive an income according to the same distribution, you save or borrow, and then you consume. So you consume what is your income plus what you saved or minus what you borrowed in the previous period, minus what you save in period 2. Again, you receive a utility, and third period, you receive an income, you take no decision, and you receive utility from consumption. So in the following, I will derive the savings functions for the constrained and unconstrained case. And this is for the unconstrained model. So we set up the maximization problem, plug in the values that I showed you before. Then we use backward induction, assume rational expectations, and derive the solutions for the savings functions. In the first period, S1 depends only on your income, or should depend on your income, and you have a linear function. I will show you later on how those look like when you plot graphs. And in the second period, it's also linear in income, but there's also entering the savings decision you took before. So your saving decision depends on wealth, which we call W2. Now to the constraint model. And the only difference that we have is that in the second period, you're not allowed to save. You're not allowed to borrow, sorry. And to make it explicit, in period 1, borrowing is still possible, it's still allowed, and now we solve that. So again, we write down the problem, and we use the same reasoning as before, backwards induction, rational expectations, and we derive the solutions to the problem. Here, this looks more fancy, but basically it's a convex function, and only one of the 2 functions makes sense economically. So if we use the positive value, savings rate explode, they're far out of the range that people should save, and only the negative solution makes sense. And in the second period, it looks pretty much the same as before, only that I have a kink. So it's also a convex function, this time in wealth. So we have predictions what people should do given their income or wealth. And let's come to the experimental design. In our experiment, we vary the existence of the liquidity constraint. So it's either con or UNCH, and the variance of the income stream. So it's either high or low. This gives us a 2x2 design, UNCHIGH, ConHIGH, UNCLOW, ConLow. And so what is important is the parametrization. When income uncertainty is high or low, in both cases, we keep the mean constant and only change the spread around the mean. So in low, you can be sure that you're, say, closer to the mean of 70, whereas in high, you cannot be that certain. And we introduce the per period utility function 0.77 LNC, and we communicated that to the subjects by giving them the formula, a table, and a graph. So we invited subjects 100 to the high treatment, and 50 to the low treatment. That's based on a power calculation. And of the 100 in the high treatment, 50 first solved this telephone. Okay, so 50 went through the treatment in the order of first playing 15 life cycles of unconstrained, then 15 life cycles of constrained, and the other 50 the other way around, constrained first, then 15 life cycles of unconstrained. And the same here. So we invited 50, 25 first unconstrained, then constrained, and the other 25 first constrained, then unconstrained. So we want to control for learning and order effects. This is what I said here. So all subjects play 15 life cycles of both constrained or unconstrained. Only one of the life cycles is chosen randomly for payoff. Subjects first receive instructions about the first part and then about the second part. They were not told what was coming in the second part. This is an example screen. Sorry for the not so good resolution. So you're told, oh, your income in this period is 82 points. This is also shown graphically. Then you're told about how much you can borrow. And then you have a slider and you can decide on how much to consume. And you know how much you save for the next period and the dollar amount that you get. Now we come to the savings functions. So let's focus on the high treatment. So second period, when you're unconstrained, you can borrow. So you have this line here. When you're constrained, you're not allowed to borrow and you should behave according to this. So we have a positive deviation for low incomes here and no difference for high incomes. You should anticipate that you are borrowing constrained already in period 1, and that's what you see here. So when you're unconstrained, it's the black line, and when you're constrained, you should save. You should always save more or borrow less, and this difference between the two is strictly positive. When you look at the low treatment, here there's also a difference. First, it's in magnitude. And the other one is that you have a switching point around 70. So you should first save more under constraint. And if you receive a high income, you should save more when you're unconstrained. So there's an interaction effect of income uncertainty and the constraint. Hypotheses. We have kind of lots of hypotheses. Basically, it's just like 6. It looks more here. So our main hypothesis is you should save more in the first period in comparison when you're constrained compared to when you're not constrained. So it's these numbers here in the middle. They're just translations of those figures here into means and standard deviations. And then we use those to calculate our predictions. So prediction H1 is in high, you should save more when you're constrained in comparison when you're unconstrained. And we use the D's here are cones, D's. We use all that for a power calculation. I won't go through all of the hypotheses because we will focus mainly I will focus mainly on this one of those two. But the power calculation told us 100 subjects in high, 50 in low, and the study is pre-registered. And now I come already to the results. So we collected the data in Irvine, you see there at the lab. Sessions lasted about 90 minutes. People received about $31 on average. And those are the numbers, the means of what people actually did. So I tried to make this easy to read. So when you look at hypotheses 2 to 6, we cannot reject them. So you save more in period 2 when you're constrained in comparison to when you're unconstrained. What doesn't work out is the anticipation effect. So here, this number should be lower than that number. That's not the case. So we have to reject the hypothesis, and the same occurs here. So you should save more here than you save here. We have to reject it. Those are this is the only set of hypotheses that we reject. We can also compare observed behavior with the predictions, and what we see is people oversave in general. So we compare the old 8.6. This is a number you've seen before here. We can compare it what people should actually do, and what we see is people save more than they expected to, and that's significant. The only two cells where they're not significant is in low in the first period. The nice thing about this experiment is that we can compare a predicted savings function and empirical savings function. This is what I show you on the next few slides. We plot empirical savings functions based on panel regressions and theoretical predictions together in one picture, treatment by treatment. What we see is high heterogeneity of savings behavior. So basically savings decisions are all over the place, especially in high. We observe already depth aversion in the high treatments, and we see that in the low treatments, where income is more certain, that the empirical savings functions are basically indistinguishable from the theoretical ones. And this is a pretty robust finding because lowest filters are not distinguishable from the linear regressions. Okay, ConHIGH period 1. Lots of information. First of all, those are all the individual jittered savings decisions, 1,500, if I'm not mistaken. And we have the prediction, the black dashed line here. We have the linear estimation with 95 confidence interval. We have natural constraints, so we have to prohibit subjects from either borrowing too much or saving too much so that their utility would become negative. But as the constraints do not affect our theoretical prediction, well, that's we make sure that it doesn't affect our theoretical prediction, basically. What we see is for high incomes, the 95% confidence interval overlaps with the theoretical prediction, and that's not the case for low incomes. You look at another treatment, unconstrained high, basically the same picture, qualitatively speaking. So people oversave here in the low income range, whereas up here for high incomes, indistinguishable. Now we come to the low incomes. So still heterogeneity, but huge overlap. So we cannot distinguish theory and prediction. Same without the constraint. I think here it's not inside the confidence interval, but the rest of the empirical estimation is within the 95 confidence interval. So we've already seen that for high incomes, or for high uncertainty, we can see something like that aversion in the savings functions. Now I will look closer into that. So maybe you're already convinced that this is good, that we have depth aversion, but now we look at the extensive margin and the intensive margin. First, we introduce a binary variable that takes value 1 if the decision is in line with theory and 0 otherwise. So we ignore the magnitude and test the extensive margin prediction of the model. We look only at period 1 of the 4 treatments, and we see that people are always more correct when they save than when they should borrow. And those differences are almost always significant here. It's like, well, 10%, we just didn't manage the 10% significance level, but we see that people are on average more binary optimal in the savings range. Now, how does this binary classification change with income or wealth. This is an example for unconstrained high. In the area where people should borrow, it goes down like this, then makes a jump into the savings range, and again increases when we're further away from the threshold. And the threshold here is theoretical threshold. And that's a typical pattern. We observe it in almost all treatments. Okay, how does the probability to behave binary optimal locally around the threshold? So what I showed you in this table is the aggregate difference. Now we look at the local difference. We have basically a regression discontinuity design, an RDD in our data. In period 1, the assignment to the borrowing or saving range is random because of the income process, and it depends deterministically on the savings function. So let's look at that. So RDD results, they confirm our results that I showed you before. So the local difference in most cases is even bigger than the aggregate difference. So that means that around the threshold, there's something going on and people don't like to borrow. Now, finally, we derive a new model that's called DA. There's a liquidity constraint in both periods. We use the same reasoning as before, and this is equivalent to perfect depth aversion. So subjects behave as if there's a constraint in period 1, even though there isn't one. And now we compare the models with our data, and we find that in high, the depth aversion model has the best fit. This is not the case in the low treatments, but you've already seen that in low, people have
Andreas, you have 1 minute left.
Perfect, thank you. So our depth aversion behavioral model fits the data best in high. And this is already my conclusion slide. So we find that the combination of depth aversion, heterogeneity, and cognitive abilities, also learning, explains this main deviation from our prediction, this hypothesis 1A and B, as several empirical studies find that the buffer stock savings model has problems explaining savings behavior. I think our results are nice because most of our hypotheses work in the predicted way, and we hope that our experimental results are informative for other research. Thank you very much. So I'm looking forward to John's discussion. Let me see whether I can